All right, so exponentials are going to be used, like I said, in the stock market. They're used in finances with like bank accounts, savings accounts, CDs, like Roth IRAs, 401ks, those types of things. They're used in populations. Now, when we talk about population, like I said, they could be population of a bank account, population of dollars, could be a population of radioactive isotopes. You guys talk about half-life in science, right? Okay, so exponentials are used there. You guys talk about Newton's law of cooling and stuff like that in science? Yeah, a little bit? Okay. Like if I have like a cup of boiling water and I put it in a room that is 70 degrees, that cup of boiling water will slowly reach 70 degrees, right? Okay. We can determine the length of time that that's going to take using exponentials. Populations of viruses, okay, that's probably something that's pretty important right now, right? All the models that they talked about at the beginning of March and slow the spread, flatten the curve, that kind of thing they talked about. Okay. All those models are using exponentials, okay? So an exponential function, simply a function in which the exponent carries the variable, okay? All the functions we've talked about so far, polynomial, linear, all that kind of stuff, the variable has been kind of in the base, okay? Now the variable is going to be a power, okay? Or an exponent. So here we're studying a new class of functions called exponential functions. An example of that is 2 to the x, okay? 2x is an exponential function. 2 is referred to as the base, okay? X is obviously the exponent, okay? One thing that we like to talk about is how is an exponential function different than maybe a polynomial function? If I look at an exponential function, I'm just going to use Excel here just to demonstrate this a little bit quicker than what my, a little bit more elaborate than what my, seriously. All right, so for something like x squared, we know that if I take x and raise it to the second power, so 0 squared is 0, 1 squared is 1, 2 squared is 4, so forth. Go all the way down to 30. The largest number we get to is 900, right? Okay, so I think we could agree that 900 is a pretty big number. 30, not relatively that big, right? Okay, so the x value, not all that big, but the y value gets large pretty quickly. If I look at 2 to the x now instead, so it's going to be taking equals 2 raised to, now that, so 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4. So this is, kind of so far behaving a lot like x squared did in regards to how fast it's getting large in the y value, okay? If I go to, so 2 times 2 times 2, or 2 to the third, gives me 8. So still, I'm not, the x squared at that point was increasing faster. Okay, 2 to the fourth is 16, so that at 4, when x is 4, these two functions are behaving the same way, right? But now at x being 5, we see that 2 to the x takes over x squared. 32 is bigger than 25, right? And if I keep going, okay, out to 10, 10 now has surpassed x squared when x was 30, right? The largest we got there was 900. Here we already surpassed that at an x value of 10. If I go down to 30, (1.1e to the positive 9. Okay, so that's 1.1 times 10 to the 9th, right? That's 1.1 billion. Okay? All I think it's like, that's actually like 1,073,000,000 or something like that, okay? Does a little bit of rounding here for us. But you see, so the largest that x squared got to was 900 when we got to 30. Here we get to 1 billion, okay? Did 2 to the x increase much faster than x squared did, okay? So when they talk about like things growing exponentially, okay, that means that they're growing fast, okay? Why did they shut down, travel from Europe to the United States back in February and March? Think about what happens with viruses. If I'm, let's say we get on a plane, okay? Let's say Andrew is COVID positive, okay? He's one person, right? He gets on an airplane. How many people are on an airplane? That's my airplane. Okay, so let's say there's 300 people on that airplane. Okay, he's one of those 300. Okay, so now let's say because of how this virus is contagious, let's say he infects. Maybe he doesn't infect all 300, but let's say he does. Okay, even if he's just infected 5 or 2. Okay, what's going to happen now that he infected these 300? Those 300 all now become what he was, right? He was a singular one getting on an airplane. Now these 300 they're all going to go get on their different airplanes, right? And what are on those different airplanes? Another 300 people, correct? Does that make sense? How fast that virus can spread? Okay. Over the next couple of days, because of what's happened recently, there's a lot of simulations online that we can look at to kind of give you the visual of how things grow exponentially. But a virus grows very rapidly, okay? Talk about cells dividing, okay? You go back to having one cell in science, right? What happens? It divides, mitosis, meiosis, all that kind of stuff, right? Becomes 2, correct? And those 2 divide, become 4. Those 4 divide, become 8, right? That division of cells is population growth, and they're increasing by a factor of 2 essentially each time. Okay. What's half-life? Okay, so if I have some like plutonium, okay, something that is radioactive, right? If I have 100 grams of it, okay, the half-life is the duration of time that it takes for that 100 grams to radioactively decay down to 50 grams. Does that make sense? And then if it experiences another half-life, it goes down to 25, right? If that experiences another half-life, it goes down to 12 and a half. Another half-life goes into half of that. And it keeps going half and half and half, right? Will it ever have 0? No. Okay. You've talked about half-lives. You've talked about some of this stuff in science. I think, like I said, I think this function is something that we don't have a whole lot of experience with and understanding of, but it is maybe one of the functions that is most applicable to the things that we do in a science class, in the medical field, that kind of thing. Okay. The point here with this Excel was to show that a slight change with an input value, the exponent in an exponential function, can cause a dramatic change in the y value. Okay, we went from, x 2 to the 5th. 2 to the 5th was 32. Okay, we go 2 to the 10th, that gives us 1024. That's a pretty dramatic jump, right? Then we go 2 to the 10th was 1024. 2 to the 30th is 1.073 billion. Okay, which is just a much more dramatic change. Okay, with just a slight change in the x values. Every exponential function is going to be written this way. Okay, and I'm going to augment this a little bit. Okay, because you can see it a couple different ways. F of x is going to be equal to a to the x, where a is referred to as our base. Okay, x is obviously our variable. You might see it written this way. Or some textbooks will actually let B, because base starts with B, let B be called the base. But we can have this number out front that is a scalar multiplier. You guys remember talking about like x squared, right? If I know what x squared looks like, isn't there a function ax squared as well? Where a could be like 2 or 3 or 4 or something like that. Does that make sense? Correct. Okay. So we could have a scalar multiplier, which is essentially a vertical stretch out in front of this a to the x. Okay? And we'll talk about, as we see the next couple examples throughout the next couple days, we can see, how do we treat that number out in front and why do we treat it that way as we move forward. But exponential functions, a value is going to be greater than 0. Okay? And a cannot be 1. If a was 1, I'd have 1 to the x, so I'd have 1 to the 0, which is 1, 1 to the 1, which is 1, 1 squared, which is 1, 1 to the third, which is 1. So whenever x is going from 0, 1, 2, 3, 4, 5, my y value would still be 1. So I'd have a horizontal line. Does that make sense? Okay, so that is why a cannot be 1. Okay. Here are just some other examples. So these are all, like, this is a parent function. This is a parent function. And this is a parent function. Okay? But they are all collectively part of another family of curves called our exponentials. Okay? So 2 to the x is different than 3 to the x, but they have so many relationships that are the same that what we learn about 2 to the x, we can transfer over to 3 to the x. And we can transfer that over to 4 to the x, and then we transfer that over to any other exponential function. That makes sense? So a lot of times what you're going to find out is that we spend a lot of time working with 2 to the x, 3 to the x, and for the reason we do that is because of how large the y values get. Just with 2 to the x, you saw the y values got very large very quick, right? If I change that to 3 to the x, they're just going to get larger quicker because that base of 3 is bigger. Does that make sense? So if we can stay with like 2 to the x, 3 to the x, and learn everything we need to know about those, then we can transition that to other functions. One of the most important bases that we will use is e, which is the natural number. Maybe in science you've talked about Napier's constant. You talked about e when you guys dealt with Avogadro's number, with molar mass and that kind of stuff back in chemistry. We'll get to that. E is, if I'm on a number line, it's between 2 and 3, closer to 3. It's like 2.8 something, 2.7 something. That's an irrational number. So okay with everybody? In general, when we talk about a exponential function, we are going to have potentially a number out front. Let's do it this way. We have a to the x. We could potentially have a number out front as a multiplier. Let's call it b in this case. Okay? And what that's going to do is produce a vertical stretch. Okay? We could have a plus or minus c up here with the x, which when we add or subtract to the x inside a function, what does that do graphically to my function? Like if I had x squared as my function, and then I rewrote it as x plus 3, that quantity squared, what's that plus 3 going to do to my graph? Shift it which direction? So if I had x squared, but then I rewrote it as x plus 3 squared, what's that plus 3 going to do to my graph? Shift it to the left 3 units, right? That's what's happening right here. Okay? Are we adding to the x right here? Does that make sense to everybody? So that's going to produce a horizontal shift And then we could have a plus d on the end here. And the plus d is going to be a vertical shift. We can also have horizontal and vertical reflections by multiplying either the x by a negative or the entire function by a negative. We'll get into that here in a moment. But every exponential function is going to be of that form. Okay? A lot of times we like to deal with the simpler variety like 2 to the x or 3 to the x. But there's no reason we can't have like 3 times 2 to the x. Okay? Let's take a look real quick at some of these functions. This is the like 1 to the x. This is why a cannot be 1. That's pretty boring, right? That's not showing growth like an exponential does. That is linear. 1 to the x is a linear function. So we start with 2. Now it doesn't have to be like an integer. I could have like 1.1 to the x. That's exponential. Okay. I could have 1.2 to the x. Okay. I'm just going to start with my integers here. So 2 to the x. We have 3 to the x. We have 4 to the x. There's 5. Okay. And you can see that throughout these graphs, okay, we can see that why do we work with 2 to the x the most? Because that one's the one that grows the slowest. Does that make sense? If I look at 3 to the x, which is the orange one, okay, its y values get very tall quicker than 2 to the x's. So, for instance, if I look at, let's just put the line y equals 9 in here. Okay, so the blue one, it takes me out to a little over 3 to get a y value of 9 on the blue one. But a y value of 9 on the orange one is an x value of 2. A y value of 9 on, let's say, this black one or gray one here is an x value of something a little bit bigger than 1. So the bigger the base, the quicker, in regards to the x values, that we get to a defined y value. Does that make sense? So that's why we like to deal with like 2 and 3. Or if I put e in here, okay, you can see that e is almost the same as like 3x. Those are very similar, right? Okay, and that's because the number e is that number right there. Okay, now it's rounded 2 decimal places. It's an irrational number, goes on forever. But that would be that base. Okay. We can see if I just talk about the 2 to the x, graph that, and I go y equals 2 to the x plus a, not a, because I already got a defined. Let's make it b. Okay, do you see how that is moving that graph up? Do you guys agree if this point was 0, 1 right there? If I add 5 to it, like that graph is doing, or that equation is doing right there, that 0, 1 should go to 0, 6. Does that make sense? Okay. This point right here at 1, 2, when I add 5 to it, comes 1, 7. So this number at the end is moving up and down. Okay. If I were to take and add b to the x, so you see now that we're adding up in the exponent, that is actually moving left and right. So what's going to happen is give you this point here and that point there. That plus 1 is actually taking that x value of 1 and moving it left 1 unit. Okay? Might be easy if I put a line here, y equals You can kind of see that point move. That's kind of a, get rid of B. Intersect. Okay, so now you can see that point as I move the B value now to 2, you saw that point there moved 2 units to the left of where it was initially, right? Does that make sense? Okay. So it's moving it left and right. Which is exactly the same as the transformations that we've dealt with every other function back to lines. Okay. When we work with exponential functions, okay, much like every other function, these parent functions, we want to have a set of points that we have memorized that are going to allow us to graph this fast. So for instance, like x squared, we know 0, 0, 1, 1, 2, 4, 3, 9, negative 1, 1, negative 2, 4, negative 3, 9, that kind of thing, right? For x cubed, we know 0, 0, 1, 1, 2, 8, negative 1, 1, or negative 1, negative 1, negative 2, negative 8. For x squared, or sorry, square root of x, maybe we know 0, 0, 1, 1, 4, 2, 9, 3. We know these collective ordered pairs that help us graph functions quickly. Well, we can do the same thing for exponentials, but we don't really want to memorize a set of points for 3 to the x, and then a set of points for 4 to the x, and then a set of points for 5 to the x. We can actually learn one set of points for all of our exponentials, no matter what the base is, okay? And it's all based off of knowing a little bit of arithmetic. If I have x to be, let's just choose 0. I'm going to put it in the middle of my list. But if x is 0, what is 3 to the 0? It's 1, right? Does it matter what that base is then when I raise it to the 0? If I go 3 to the 0, I have the point 0, 1, right? If I go 5 to the 0, is that still the point 0, 1? 5 raised to 0, still 1? So no matter what my base is, I should, when I raise it to a 0 power, I still get 1 back. So what that tells me is that every one of our exponential functions, 2 to the x, 3 to the x, 4 to the x, 5 to the x, e to the x, pi to the x, I know that every one of those is going to have the point 0, 1 on it. Does that make sense? Okay. Now, let's try the x value of 1. What's 3 to the first? 3. Okay. Let's say my base was 2. What's 2 to the first? 2. Let's say my base was 12. What's 12 to the first? 12, right? So isn't that point right there, 1, 3, isn't that just 1, whatever my base was? Okay. So this chart here is for my specific 3 to the x. But this chart here is for all exponentials a to the x. We'll have the point 0, 1. We'll have the point 1, whatever your base was, 1, a. And now another point that I want is if I try negative 1. What's 3 to the negative 1? If I have 3 to the negative 1, how do you rewrite that? So you don't have negative exponents? Seen that before? Rewrite it as 1/3. So 3 to the negative 1 is 1/3. What is 1/3 in comparison to my base? It's its what? It's its reciprocal. It's multiplicative inverse. Okay? So if I have negative 1, this is just, so if a was my base, then 1 over a, by definition, 1 over a is its reciprocal. Okay? So if I can remember that blue chart, being a first in my exponential, determine what a is. And remember that blue chart, I should now have 3 points on every exponential function I ever come across. Okay? So if we plot these, I'm going to plot on GeoGebra, which is a little bit easier. So we had 0, 1. We had 1, comma 3. And we had negative 1, comma 1/3. And those, so once I have those three, I'm going to have y equals 3 to the x, pass through that, and there would be my curve. Okay. Now, think about this. As I get more and more negative, we're going to do this with Excel as well. Should be a little bit easier. So let's say x is negative 1, negative 2, negative 3. See if we get that pattern to continue. Okay, and then I go 3 raised to that. So there's 1/3. Here should be 1/9. There's 1/27. Okay, here would be 1/81. Okay, so what I'm getting here is 1 over a larger and larger denominator each time, right? Well, if I keep doing that, what are these numbers getting closer and closer to? Yeah, those are getting closer and closer to 0. So as x goes further and further out in the negative direction, my y value is getting closer and closer to 0. But I'm always going to have, so in that last one, negative 28, I'm going to have 1 over 3 to the 28th power. Well, 3 to the 28th power is a very large number, right? 1 divided by a very large number is something, but it's very small, correct? I still have an amount, but it's getting closer and closer to 0. So what does that tell me? As x goes this direction, what is this x-axis playing for us? What is it behaving as x goes out this direction? If I zoom in, okay, so your x-axis is playing the role of a horizontal asymptote. Okay, and it happens right there. You can see that there is separation between them out here at what, negative 19. I'm not even very far, negative 20. But no matter where I go over here, I should be able to zoom in and see there's a gap between the graph and the x-axis. So it plays as a horizontal asymptote. Is that okay with everybody? So every one of our functions is going to behave that way. If I have, instead of 3 to the x, let's just go a to the x. Is that x-axis a horizontal asymptote for all of these? That makes sense? Okay. Now we can flip it. You can see now this is exponential growth right there. Because as I move from left to right, my y values are increasing, right? This is referred to as exponential decay. So you guys talked about half-life in science. This is the curve we're talking about. Okay. Let's talk about that real quick. Let's come over here and look at something like 1/3 raised to the x. Okay, 1/3 raised to the x. If I go off of my parent function, I should have the 3 points, -1, 1 over a. What is my a value for this g function? 1/3. So 1 over 1/3, 1 over 1/3 becomes 3. 0, 1, that's going to be on every one of my exponentials. And I have 1, comma a. Well, 1, comma a was 1/3, so I have 1, comma 1/3. If I plot those, -1/3, 0, 1, and 1, 1/3, my x-axis now, as my x-axis gets larger and larger in the positive direction, okay, I'm going to have 1, so 1/3 raised to the x, that's the same as 1 to the x over 3 to the x, right? But what is 1 to the x no matter what x is? Just 1, right? So when x gets really, really, really big, okay, so I have 1 over 3 to the 10th, 1 over 3 to the 20th, 1 over 3 to the 40th. I'm having 1 divided by a very, very, very large number. And now, as we move to the right on the x-axis, we are approaching our horizontal asymptote of y equals 0. So, let's graph y equals 1/3 raised to the x. And compare that to 3 to the x. Change the colors here. All right, so the blue one and the red one. Red one is 3 to the x. Blue one is 1/3 to the x. What do they look like they are to one another? One of them looks like the reflection of the other across the y-axis, right? Go back to transformations, chapter 2. How do I get a graph? Let's just say that we're going to start with, like, let's just go y equals x plus 4 or x plus 5 squared. Let's say I start with that thing right there. How do I get its reflection across the y-axis? What do I need to do to that equation to get a reflection across the y-axis? Anybody remember? Put a negative sign where? If I put it there, did that reflect across the y-axis? No, that was the x-axis, right? So I need to put it on the x, and that reflects across the y-axis, right? So, what does that mean here? That means if I take y equals, let's just go 3 to the x, okay? And I take and make that, instead of 3 to the x, make it 3 to the negative x. This blue one changed for some reason. All right, so we started with these 2 red ones. These are the only 2 that I have highlighted, right? Okay, they are reflections of one another. Okay, now if I type in this green one, show the green one is the same thing as that 1/3 to the x. Does that make sense, everybody? So let me delete this one real quick. These 2 graphs right here are identical. They are the same exact thing. Sometimes you'll see it written as 1/3 to the x. Sometimes you'll see it as written 3 to the negative x. Okay? Just depends on the author's preference. Let's talk about why they're the same. We already did a little bit of this algebra. If I talk about f of x equaling 1/3 to the x, laws of exponents tell me I can rewrite that as 1 to the x over 3 to the x, right? Okay, all I do is I multiply those exponents of the 1 and the 3, correct? But 1 to the x is, no matter what x is always 1, right? Does that make sense? Did we have the ability with laws of exponents to rewrite this as 3 to the negative x? Does that make sense to everybody? So, 1/3 to the x is the same thing as 3 to the negative x. And that then allows us to make the connection that if I know what 3 to the x looks like, if I know what 3 to the x looks like, and I know what transformations do, multiplying x by a negative is a y-axis reflection, I should be able to find out what 1/3 of the x looks like because of that. Okay. Over the next couple days, we're going to go and investigate these exponential functions. We're going to graph a lot of them. We will see them in applications. The one thing that is very important, does anybody know how to graph a logarithm? That's the next goal. That's our next task. We'll probably get there by like Thursday, Friday this week. You cannot graph a logarithm if you do not know how to graph an exponential. Does that make sense? So you will be up a creek if you do not know how to do this. Okay? 0, 1, 1 comma a, negative 1 comma 1 over a are the 3 points on an exponential that we need to know so that eventually we can attack logarithms as well. Okay?